All right, PreCalc, another hopefully short one here. 1.10, modeling with functions. You're going to love this word modeling. Usually means story problems. So, we're sophisticated college prep class here. So, of course, we don't want to say something so simple as story problems. So we call it modeling. All right, so let's go through. Let's do some practice ones. And again, my philosophy here is whatever the type I practice with you would be the type that would show up on a quiz or test. So that's what you want to know. So functions from verbal descriptions. Write a critical sentence that describes the function conditions in terms of its independent variable x, and the verbal model can be translated into algebraic notation to represent the function's equation. Okay. Fancy way, we're going to model with functions instead of equations, so we're going to see a lot of f of x or p of x or q of x or whatever it is they want us to use. So a lot of this is more kind of tailoring things to the type of equation or what they ask us to do. Okay, so in example 1, and I did not make this up, okay? I did get it out of the book. According to the National Center for Health Statistics, in 1990, 28% of babies in the U.S. were born to parents who were not married. Throughout the 1990s, this percentage increased by approximately 0.6 per year. And A says express the percentage of babies born out of wedlock, P, so instead of f of x, we're going to do P of x, that's what that's telling us, as a function of the number of years after 1990 x. So they're choosing our variables for us. P is the function, x is the variable, and the x is standing for number of years. Okay, so that's kind of where we have to start with. So as a function, P of x. Okay, so currently we have a set number they gave us of the number of percent of babies born out of wedlock. Okay, now our equation would look really difficult if we try to put percent in it. And I'm going to be honest too, I know 28% can be written as a decimal 0.28, but because everything we're talking about is percentages, we're going to just leave that a whole number right now. Okay, so we started with 28% of the babies, and it says that they believe it's going to increase, so there's a plus, by, and this is important, the percentage is increasing by 0.6 each year. So again, as a decimal, if I said an increase of 0.6%, you have to think about that. That would have been like 0.006, right? But because we wrote the 28 as a whole number and not as 0.28, we also can write that 0.6 just as it is. So I'm going to just do 0.6 for every year. Okay, there's my function. Okay, so that's all they're asking me to do right now is just to write the function. Now for B, it says if this trend continues, in what year will 40% of the babies be born out of wedlock? So now we can work with 40%. Again, I don't have to change it to a decimal because I didn't earlier. So 40% is the number of babies over here in for my P of X, or my quote Y, right? Equals 28 plus 0.6x, and we are working on solving it. Subtract 28, I get 12 divided by 0.6. Remember, that's like 120 divided by 6, right? And that would be 20. Okay, so what does this mean if we get x equals 20? Well, remember it said the number of years after 1990. So 1990 is where we start with, 20 years later, and we get 2010. So my final answer, if this continues in what year? Well, my final answer would be in 2010. Now, obviously, this came from data and a story problem that was written a long time ago. I say that right. That doesn't seem like a long time ago, 2010, but it's been 10 years. So I don't know. It'd be interesting to go find statistics and see if that matches. So in your free time, go look it up. All right. Moving on to example 2. All right. And I was just peeking here in example 2 because I know sometimes I give this story problem and sometimes I'm like, why did I use 100 twice? It makes it confusing. So make sure you kind of follow what I'm saying here so that you can apply it to the problems you're doing, and I'll try to kind of over mark it too so you know what this is. Okay. On a certain route, an airline carries 8,000 passengers per month, each paying $100. A market survey indicates that for every $1 increase in ticket price, the airline will lose 100 passengers. Okay, so we're going to model this with a function. Notice the number of passengers, they want it to be n, so we have n of x, okay? All right, so what do we start with? What's the set amount? And that's my 8,000 passengers. Okay, now, the ticket price is x, okay? And we have to be careful. So x is the ticket price, right? Now, it says that for every $1 increase in ticket price, okay? So if we have a set number, like we say, oh, now the ticket costs $110, we know that's $10 over X, okay? So the best way to know the ticket, how much over the $100, is we're going to represent it by X minus the 100, okay? Because the 100 is a set price. That will give us right now the amount over 100, okay? So this is the starting, and this is the amount over, okay? That's what it's going to find us. All right, so it says we're going to lose 100 people. Okay, so this is the people lost, right? We're going to lose 100 people for every dollar increase in ticket price. So that's that X minus 100 we just found. Because the 100 isn't going to lose us anything, but every cost over that, okay? All right, is that kind of making sense where we came up with those? So if that's all I need, I can stop right there, okay? But for B, it says express the monthly revenue for the route in R as a function of the ticket price. Okay, so first I need to find, I'm going back to my N of X, and I'm just going to clean up this function. So I get 8,000 minus 100X plus, when I distribute my 100, I get 1,000, right? No, I get 10,000 if I could multiply correctly, right? Okay, so cleaning this up, let's make it look like a function. I'm going to put my variable first. Negative 100x plus 1,000. Sorry. Blah, blah, blah. All right, there's my N of X. That's how much the airline is making, okay? So if they sold, for every, $5, increase, then it would drop at $500, when we plug it in. To find the revenue for that, we need to take all of these passengers, because that's what this is right here. These are passengers, the number of passengers, N. If we multiply it times X, the number of tickets we sell, then we can find the revenue for this. Okay, so now we're going to change over to revenue, and we just multiply everything X. So we get negative 100X squared plus 1,800X. This is the number of passengers, N of X. When we multiply it times the X, the ticket price, then we can know how much we actually made. So there's my revenue now when I multiply all of that times X. All right. I have in my mind how I need to explain it, and then my tongue gets tied up, and I probably confused you more than you needed. Okay. Let's look at example 3, a little bit of geometry here. A machine produces open boxes using rectangular sheets of metal measuring 15 inches by 8 inches, okay? So here's my sheet of metal, 15 by 8. Okay. The machine cuts equal size squares from each corner, okay? So all of these corners, we cut out the square, okay? And if you can visualize it, what that does is we can fold on these lines, right? And when we fold on these lines, we end up making this nice little box, right? We fold up on those lines, and we can make a box. It's open in there, okay? So now we have to think about, and it shapes the metal into an open box by turning up the sides. Express the volume of the box in cubic inches as a function of the length of the side of the square cut from the corner X. So we don't know how big of a square they're cutting, but we know because it's a square, all of these little things are X. All these little corners. Okay, so think about it. This side right here used to be 15, but I'm cutting out 2 corners of it of 2x, because think about it, this is my new length in here. If you think about this, this is what I'm doing. So this mark right here is 15 minus 2 of the x's. So I'm going to put it down here, 15 minus 2x, okay? And so my width over here, my new width, is going to be 8 minus 2 of the x's. And then if you think about how high the box is, well, that's this little part here when it folds up, and those are all X, okay? So there's my new box. Those are the dimensions of my box because of that corner being cut out. So how do I find volume of a box? Well, volume is length times width times height, okay? And remember, it doesn't really matter which is the length, width, and height. So my V, I should put this in function notation, V sub X, not V sub X, V of X. I need to be careful there, is going to be 15 minus 2x times 8 minus 2x times the height, which is x, okay? And if need be, multiply those out, okay? I'm going to actually just stop it right there because if I need to find something out, like actually plug in some numbers, I'll do that, okay? The second part, though, is something we really need to stop and think about. Find the domain of V, okay? I can't plug in any old x I want. Obviously, can I plug in anything 0? We can't have a 0 height on this box or it won't be a height. So I can't, 0 is like the lowest, but I can't really be there. So I'm not going to include it. So I'm just going to put my parenthesis there, okay? And now the question is, what's the absolute highest I can make? Okay? This is really 15, 8. 8's going to be my limit here. Think about what x value there, that 8 minus 2x. I have to keep it larger than 0 because I can't make my side again 0 or anything less than 0. So I got to be bigger than 0. So I can subtract 8 here, and I get 8, negative 8 divided by negative 2, and that flips my sign. My x needs to stay smaller than 4. So I have a domain here, and notice I need to be smaller. I can't be 4 or I'd end up with that 0 side. So my domain needs to be between 0 and 4 to make sure I still have a box. If I try to do anything beyond those two, then I wouldn't have a box. All right? All right, second page. Another kind of geometry one here a little bit. You have 200 feet of fencing to enclose a rectangular garden. Express the area of the garden as a function of one of its dimensions, x. Okay, so rectangular garden. I know there's 200 feet total here, okay? So around is really perimeter. So let's keep that in mind. 2L plus 2W is my around or my perimeter. And I know my perimeter is 200, okay? So it says as one of the dimensions is x. So it doesn't matter which one you plug in, just make one of them x. So let's make my L x, okay? And I'll make my W, just leave it there. Okay, so if my L is already x, okay, I need to write, sorry about that. I need to write, I don't know what I'm doing, my width in terms of x as well. So let's solve this equation for my w, okay? So I'm going to first subtract 2x. So I get 200 minus 2x equals 2w. Divide by everything by 2. And I get 100 minus x equals w. Okay, so my length here is x, and my w is 100 minus x, okay? So each of these sides, x, x, and 100 minus x, okay? That gives me both of my dimensions in terms of x. So now when I want to find the area, a, of x as my function, well, area, remember, is length times width, so it would be x times 100 minus x. And again, if I want to, I can distribute that out. I can get 100x minus x squared. If you want to write it how a nice function looks, you can write it negative x squared plus 100x. I mean, options here, right? And again, I'll try to make sure I tell you, like, please multiply it out, or you can just leave it as, you know, the multiplication or something like that. The key thing is making sure your variables both go into the same using that x, okay? All right, next one. Your grandmother needs your help. She has $50,000 to invest. Part of this money is to be invested in non-insured bonds paying 15% annual interest, and the rest of the money is to be invested in government-issued certification of deposit paying 7% annual interest. Now, as a young person, you're like, why would anybody invest in 7% if you could get 15%? But the key there is they are non-insured, which means there's not a definite guarantee that you're going to get the 15%. That's the average they're earning. And if something happens to the stock market or our economy, that could all change. So it's a risk, but sometimes it's nice to go for that big amount and hope for the best. But again, this government-issued CDs, those are a lot safer. Once you lock into a rate, the rate has to stay for the length of time you locked it in for. So as you invest, there's different options. Some pay more than others, but some are riskier than others, and that's the risk you take, okay? So we want some of it in the 15%. How much do we want in 15%? I don't know. Let's say X. let's put x in the 15%. Okay, so how much are we going to then put in the 7%? Well, if I put x in the first one, I have 50,000 minus however much I put in the 15% left for the 7%. So that's what I have. So it says for A, express the interest from both investments, I, that's going to be my function, as a function of the amount of money invested in the non-insured bonds. And I guess good thing we put X on the non-insured because that's what it told us to, and I didn't look ahead. Okay, I of X. I'm going to get 15%, and this time I will go for that percent, that decimal, of X plus 0.7% of the 50,000 minus X. Okay, so that's going to be the interest I earn is off of this money. So I'm good with A. That's all I need is a function that represents what I'm going to earn. Okay. Now for B, it asks me, it says your grandmother told you she requires $6,000 per year in extra income from both of these investments. So how much should be placed in each? So she needs her interest to be $6,000. Okay. So I'm going to replace my A of X with 6,000. And I have a nice algebra equation to solve here for X. Okay, so I'm going to get 0.15X. Over here, I'm going to distribute my 0.07. That gives me 3,500 minus 0.07X. My 0.15X minus my 0.07X leaves me with 0.8X, 0.08X. Subtract my 3,500 over, get 2,500, divide by my 0.08, and it looks like I need $31,250 in my 15%. So I need $31,250 in the 15%, the non-insured. And if I do a little subtraction from 50,000, that leaves me my 18,750 at the 7%. All right. Wow. You can tell what that symbol was, huh? All right. Set up the function, and when needed, plug in what you need to solve it, okay? All right, last one. And I am going to tell you, I like this one. I'm going to stress that you know and you practice this one because I do believe this one's a good one to know what to do with. Okay, let P of X be a point on the graph of Y equals the square root of X. Okay, visualization here. Y equals the square root of X because it's a square root. 0 is the smallest number I can plug in, right? And then, like, if I plug in the square root of 1, I get 1. The square root of 4, I get 2, right? It's this graph like this. Okay. So I have P, which is a point somewhere on this graph, okay? I'm going to change my color here so you can see. I'm going to just say this is my point P. I don't know this point, right? It's some X and it's some Y. And I want to find the distance from this P to 1, 0. So here's 1, 0, okay? I want to find this distance right here. And I want to make it a function as the point's X coordinates. So I'm working with X, okay? So quick note here. I have X and Y here. I don't want X and Y, okay? So I know my X is X. But if I plug in an X up here, so what do I get when I plug in X for X? Well, I get the square root of X for my Y. Does that make sense where that's coming from? I get X and the square root of X, okay? And that way, if I tell you later that my X was 7, then I'd get the square root of 7 for the Y coordinate that goes with it. If my X was 204, then the Y would be the square root of 204. So that's kind of represents everything in terms of X. Okay, I'm going to find the distance formula now because that's what I'm finding, the distance between my 2 points. So remember, it's the square root of my, subtracting my X's. I'm going to do X minus 1. Squared plus subtracting my y's, which is the square root of x minus 0 squared. Okay, what can I clean up? I can't do much with x minus 1 at the current. Square root of x, when I subtract here, I just get square root of x squared. Okay, let's square them. Let's see if we can get any like terms. Square root of x x minus 1 squared, I need to FOIL and get x squared minus 2x plus 1. And then the square root of x squared is x. All right, I do have two like terms. So I get x squared minus x plus 1 when I join my like terms. And it's all under the square root. I can't do anything more with that. So now my distance is what I'm left with here, okay? And yeah, it seems kind of funny. It doesn't have a real clean answer. But again, if I just tell you that for my p-value, that I have a value of, say, 9, I can plug in 9 and do 9 squared minus 9 plus 1, take the square root. I have the distance of the whole thing, and I'm good. So I basically have shortcutted it so it's just a plug and chug once we get a value. Okay? So those are our modeling with functions we're looking at right now. Practice on page 261, 3 through 48 by 3s. All of these type that look like the ones I did are open game for the test next week. So practice them. Let me know if you have questions, and we'll look at some in class if we can be in class together.